6 years. This is my wife Sunanda. Okay. They wanted to make sure that this is my last class and I won't come back to, right? This is my daughter Madhvi. I'll have them talk for themselves for 5 minutes. Tell you about yourselves, tell about yourself, okay? And here, oh, that's your, okay.
Like he said, I'm his wife for 56 years. And when we came here to 1977 to MMC campus, there were only 3 buildings. So now you can believe how many campuses and how many buildings. So this is our daughter, Dr. Madhavi Chandra.
So that's why he brought an entourage today. It's because it's bittersweet and mixed emotions, but today is his last actual lecture. So you all don't realize how lucky you are to be part of history, because he's been teaching here for 46 years. I can't count. I was trying to count the number of master's students and PhD students that he has graduated and undergraduates that have gone through his tutelage. But today marks a really special day for us, so we wanted to be here. I actually live in North Carolina, but was able to come here. So you probably surmise the essence of my father, right? He's an educator at heart, but he's just embodies kindness and compassion, and he really, really cares about his students. When I was growing up, when I was in like middle school and high school, we used to have students call the house and ask, we didn't realize he was writing our home number on the blackboard at the time, and students would call the house and maybe Dr. Subbarao Wunnava there, and I'd give him the phone, and they're physically asking him a question about homework. And I was like, oh, okay, so this is what college professors do. And then sometimes there would be students literally around our dining table having office hours, like on a Saturday afternoon in our house. And then we really thought that was normal, because I was still not in college yet. Then I get to college and I'm like, oh wait, this is not how this works. I was expecting home phone numbers on the blackboards from my professors, but that's not what happened. So that's just what we saw. And so I'm happy to be here, and I hope that you all embrace the opportunity that you have to be here with him today. Thank you.
Thank you. Thank you all.
Oh, okay, that's good. Thank you. David, you have to talk to the class or not necessarily? You don't have to talk to the class, right? Do you have to talk to the class?
No, maybe just for a few seconds, just to let them know what we're doing, yeah.
I paid you for life. What's the matter with you? Okay.
So if you see me or our videographer back there, Nico, walking around,
Hey, you people owe me project as well as report on 3-phase. Madam, what are you collecting? This one, keep going. Okay, put the Subbarao farewell to FIU, and then we'll go back to the RF, okay? Yes, madam? So, did you collect the reports? Today, Dr. Roy could not come because he had something else, but he said hi to you people too. So you people know, huh? Oh, he's a great man. So I'm going to give you test 2, which is also the final next Tuesday, right? And as I said, it's going to be open book and open notes, because we don't believe in you memorizing equations or anything. Okay, but at this is okay. Come prepared. So a lot of people once again sent me the email, this and that. Whatever we have covered in this semester, saying I'm Subbarao from the very first class, up to what we would be finishing up today. That's number one. Number two is open book and open notes. Don't waste time. You should know where the material is, right? Number three, did you give a professional project for me or a lousy project? Huh? I'm going to show it to Dr. Roy. That's what I'm saying, okay? And I'll give you back these things Tuesday. And are you participating in the senior design project displays? No? Talk to your student representatives, because today and tomorrow there are demonstrations of your seniors, what projects they have been doing and they have been displaying. Dr. Roy and also our chairperson said to encourage you people to participate in those, because you learn what they have done and what you could do. And so we're going to go into some material, what we have done here. And today also I would like to introduce the applications of artificial intelligence, because artificial intelligence is a big, big name. Everybody gets confused. People who talk about it get confused, right? But what is most important is we discuss artificial intelligence is nothing more than looking into a database, coming up with a commonality. Is that clear? And then project what you want to do. In calculus, we have an advantage. We can extrapolate, right? So same thing, whether you are making a building or whether you are making an air conditioning for an office, depending upon how the progression is, you predict what will happen. That's what the artificial intelligence, right? Okay, today let's get moving. We should thank these girls for giving me heart attack, but at the same time, helping. We have to thank Len, because every time I had to ask him to put my material, right? You do that in industry, you will see what happens to you, okay? We are hired for life. Okay, today any questions you have about the test 2 I'm going to give you? I'm not giving the questions for sure, but you should know everything what we have done. That's what Dr. Rohik told me. It's open book and open notes, don't get worried, okay? Oh, yeah. And from there I'll take it up, but I'll put it in such a way I'll confuse you. So if you try to duplicate, that's what our teachers did for us. Okay. Now, if you know the material, don't worry about it, right? Okay. Because you see, it's not me, it's the system. Is that clear? It's the system. David, you want, or can I proceed? Okay, that's good. Give me a couple of more minutes. Okay, did you see what I have put in here? This is for you people. Madam, come here. How do I get rid of this? Not the one, this one. That's all?
Yes.
Okay, ladies and gentlemen, this is what I wanted to say to you people. And people like me have grown with FIU and also industry, but basically my sincere gratitude to you, FIU colleagues, administrators and students. And if you think that the people like me caused you any anxiety, come and talk to me and I'll cry with you, okay? No, right? And no, if I made any mistake on the grades, I already corrected it. But if you still think there is something missing, you can always come and talk to me. I'll be here Tuesday is our final exam, 12 to 2. But I'll be here Tuesday about 9 o'clock. I would say 10 o'clock. So, but before you ask me to give you an extra point, you show why I should. If you try to trick me, I'll take out 5 points. Is that clear? That's not me, that's Dr. Roy. Okay, now let's see what we got. Okay, special assignment on 3-phase power. So people gave it to me, right? Okay, so people are good. April 25th, I don't have any authority to change it because it's a university curriculum. And we have got the final exam between 12 to 2, right? And I do have the permission from Dr. Roeg and the department. It's going to be open book and open notes, okay? And no neighbor, no using your cell phone to communicate with third party, because there were 2 or 3 people told me last time you did it, please don't do that. It is your honor, your career, okay? If you don't know it, it's all right. But concentrate, do the exam the best you could. That's what I'm up to, madam. And then I got to go to, let's see what else I have. You had to come here. I paid you for life. What's the matter with you, madam? Go back to this. Yeah, go back to the modules. Okay. Steganography, everybody felt good, right? You do it at home, because I'm surely going to pick up something from there, because nowadays with all this data security, not only just, FIU, everywhere, people are looking at second, third level of data security, and steganography is one of them for sure. So make sure you understand it, and you could use it in your other classes, okay? So definitely I'm going to pick up something from what we discussed in this. This gentleman, Richard, I tried to contact him again. He's too busy with the Dade County. He is the administrator for the security measures. And he said he would come at 3 the other day, but 3 o'clock doesn't mean anything for us, right? Okay. But we'll see if he comes. At least I will have him videotape something for you guys. And now let's go into the antennas and RF. Hey, you got to excuse my beautiful writing, okay? Did you read this? Be honest, okay? You didn't want to read it. What if I pick up some questions from here, intricate? Okay, never mind. Nowadays, unfortunately or fortunately, almost every unit, including your PCs, cell phones, everything is RF, right? You got communication through the internet, not internet, excuse me, radio frequency. How are you getting the signal?
Antennas.
What is an antenna?
Receiver.
What are the elements of antenna? Is it a piece of wire, or is it RLC? Everybody keep in mind, whatever we do, all these antennas are nothing more than inductance and capacitance to filter out the frequency. Then the resistive component is needed for us to generate the power. Is that clear? Okay. Resistance is the one which does all the work. So wherever we go, you will always be with RLC. So let's go little by little on this. Okay. So this is an antenna. This is a typical way of representing antenna. So the atmosphere has all kinds of electromagnetic signals. Is that clear? You cannot say it's only my frequency, but it's all the frequencies. I tried to get a number from Motorola. They said, Professor, why do you need that information? I said, hey, we got to share with the students. And they themselves do not know the electromagnetic spectrum in the air. That's what they told me. Meaning that the whole thing is nothing more than electromagnetics. How come we don't see it? Huh? Yes? Huh? Or in other words, the frequencies are not within the human bond, right? Okay. So when we're talking about all kinds of frequencies around, when we design the antenna, we try to customize what we need. That's what these people were saying, Motorola or Intel, anybody. So this antenna, why we represent as a 3, it is covering all the space. That's what it is. Okay, here the statistical analysis says the approximate voltage, these are all RMS, okay? Doesn't matter what the frequency is. This is, we are talking about the root mean square value, right? It is not 60 hertz, it's into thousands of megahertz, because once you transmit, that's what the frequency range is. So this antenna is covering, and the signal coming out is 1 microvolt. Do you see that? 10 raised to minus 6 volts. Now they were saying it is even down to 10 raised to minus 8. And I don't have a lab to check it out. But right now, if you have to scale it down, you could. But let's talk about 1 microvolt of signal coming in through the antenna. And one of the things they always want to do, the antenna is broadband, so because it covers all the signals which are available, but we have to custom tailor them to what we need. Here is the broadband amplifier with a gain of 10 raised to 6, meaning you don't put one amplifier with 10 raised to 6 units of gain. System gets into oscillations. So you'll have 3 to 4 things. When we got from Motorola, we have 3 stages. Each stage has a gain of 100. So each time you have it, keep this in mind, okay? Once you couple 2 systems, you should have a negative feedback to make the systems, overall system stable. Is that clear? Otherwise, you get into oscillations. It's our responsibility to do that, right? When you put a negative feedback, you compromise a part of your gain. So you design for higher gain, put the feedback, make the system gain what you want, right? You understand what I'm saying? So here, even though we are showing 3 stages, but the overall gain is 10 raised to 6 units, okay? If it becomes unstable, make it 4 stages or 5 stages. Usually, they want to go 3 or 6, okay? Don't get into any kind of further details. But right now, when I got a gain of 10 raised to 6 units with 1 microvolt coming in, we are talking about a voltage coming out of this panel at 1 volt. And we approximate at 0 degrees. It doesn't matter what the phase angle is, but we assume to be 0. Is that clear? It could be anything. So proportionally things will change. Then the most important thing is you want to only let the frequency what you want to pass through the next stage. Here we're talking about f is equal to 100 megahertz. That's what we are talking about. 100 megahertz frequency we are tapping out. Omega, the radian frequency is 6.2 pi f is 628 megaradians per second. This is pretty much industry standard nowadays, okay? And once you design the systems to check on certain frequency, so this is the frequency what the industry checks out, okay? And then, the value is of course 10 raised to, if you look at the sinusoidal content on this, it is 10 raised to 6 sine 628 into 10 raised to 6 volts. This is exactly what you see if you have a spectrograph of that kind. You can clearly see that. But right now, FIU doesn't have that kind of a capability. Hey, don't get me wrong. Okay? But if you want to do that, you go to a company like Motorola or Intel, then they can show it to you, right? Okay. As a matter of fact, you should take it as a design project for yourselves. Damn thing. Invent one, right? All right, coming back to this. So once we process the antenna and the broadband amplifiers, we got 1 volt at 0 degrees. Then we run it through an LC filter. Do you see that? And a series LC, at resonance, it's a short circuit. At any other frequency, it's an open circuit. Do you understand that? Series LC is a short circuit at the resonant frequency. Any other frequency, it blocks the signal. You understand this or no? You're supposed to have done that in your project. Did you do that? Yes. I'll see if you have done it or not. I have your phone number, I got your email, I know where you live. Is that clear? Oh yeah, we'll see what it is. No tricks. Why not? These, are you friends with them, madam? You don't know who they are? You don't know them. I'll see your report. We'll see. No, what I meant to say, ladies and gentlemen, this is the most important thing. Afterwards, we scale it down. So I'm letting the 100 megahertz pass through, which is 628 megaradians pass through. So here are the calculations. This is where you want to do. And we are cheating a little bit because we assume ideal components. Is there anything like ideal? No. But towards the end of your design or whatever it is, you specify subject to plus or minus 4% or 5% variation. Right now, this is all right to do the calculations using the ideal components. So coming back to this, we got an LC filter, only let that 100 megahertz frequency pass through. So putting the values for this, the radian frequency of course is always 1 over square root LC. Putting the requirements, you calculate the inductive value to be 1.6 microhenries for this particular frequency, the C to be 1.6 into 10 raised to minus 12 farads. And if you don't like those numbers, of course, we can change them. And the most important thing is the resonant frequency should be equivalent to 1 over square root LC. Is that clear? So if you want to change the values, you could, but the resonant frequency you cannot change because that's the one we are getting from the antenna. Okay. And you may have to try these things in a lab. So putting the values, ladies and gentlemen, and so with these values, the inductive impedance is J 1000 ohms. The capacitive impedance is minus J 1000 ohms because they are in the series path. J 1000 minus J 1000 is 0. Is that clear? Before you try to release any of your designs commercially or third party, you check it out and see whether the signal transmission is there or not. Whose responsibility is it? You, not me, not Rohit. You guys. Is that clear? What? Come and see me at the class, madam. Okay. Now, what I meant to say, before you release the designs, it's okay in the classroom or labs, but a lot of you are going to go into industry or grad school or medical school. Before you release your product, you should be absolutely clear about their response. Is that clear? Okay. Now, putting these things, we got them. So the frequency response curve, I'm not going to spend time on this because you people, this is the way you should always portray. So right at the resonance at 100 megahertz, we peak out because everything goes through. If I have 10 volts RMS at that, and the points of interest for us are 1 over square root 2. This is universal, except 2-3 countries in the world. Everybody follows this pattern. Peak and the 3 dB points which refer to 1 over square root 2, so which is 707 points we call it. So the bandwidth is determined between these two. Okay? And one of the most important things we should do, I was talking with Dr. Rohit the other day, and also a couple of our colleagues from Florida Atlantic University, before you release any RF designs for the outside, you should check inside 2, 3, 4 different ways. Is that clear? To make sure they are consistent and they are absorbing the signals and letting the signals pass through what you need. Right? It's our responsibility. Because once you release a product, that becomes kind of terrible to call them back. A 5% recall is equal to putting a new product. Keep that in mind. Is that clear? So it's our responsibility to make sure the designs are appropriate. Now let's get to this. I want you people, I'm going to give you a question on this, but I'm not going to discuss on this. You people do it. You people are too lazy, okay? Go home and redo this. No? You don't trust me? Yeah. Okay. The most important thing, ladies and gentlemen, I got a positive feedback. Do you see that? This is called Schmidt trigger, and I got a negative feedback, and the whole thing becomes an oscillation by itself. Okay? And the frequency is determined by the value of C and your R. Usually when you got a system like this, nowadays unfortunately we are doing little too much of a digital, and so this is a digital oscillator with this kind of a scenario, and it is called Schmidt trigger, the positive feedback. The negative feedback is to to fight over the positive feedback. So interaction between negative feedback and positive feedback makes the system oscillate, controlled oscillations. Okay? And I want you people today, I'm going to give you a 5-minute break before you go to Miami Beach or any place. redo this, madam. Redo this. Is that clear? And don't blame me or Roy Tuesday. Okay? So here, the most important thing is, this is a square wave, but anyway, the important observation for us, let me ask one thing. Going back to your Fourier series, I have not put it here. If I have a square wave of frequency, let's say 1000 kilohertz, not that, but in general, if I have a square wave whose frequency is 1000 kilohertz, right? Does it contain a sine wave component? How do you build a square wave? Don't tell me I got an oscillator. But from a mathematical point of view, from Taylor series, what's the relation between sine waves and square waves? Square wave consists of sine wave, third harmonic, fifth harmonic, seventh harmonic, all the way. But usually in electronics and systems, we terminate at seventh or ninth harmonic. So a square wave is fundamental, frequency, third harmonic, fifth harmonic, seventh harmonic, ninth harmonic, keeps going. So what I'm saying, ladies and gentlemen, if you put appropriate filter, you could certainly make a sine wave out of it. But what I'm trying to tell you people is, in reality, when once you have the oscillations, you try to figure out the filters, what you would like to extract from the square wave. So here, the numbers I have shown you, as per this particular scenario with the numbers what we have put, the frequency of my square wave is 5 kilohertz. Now let me ask you one simple question. You people sent me some emails on that. We have designed an oscillator for 5 kilohertz. I want to make it 50 kilohertz. What do? It's designed for 5 kilohertz. I want to make it 50 kilohertz. What do? Do I increase the capacitor value by a factor of 10 or reduce it by a factor of 10? Huh? I got to charge it faster, right? If I get higher frequency, I got to charge it faster. If I have to charge it faster, should I increase the value of capacitance or lower it? Why did it take so much time? You people didn't read it.
I said reduce it like right away.
Oh yeah? Did you?
I did.
Okay, take 10 points from them, okay? See, I'm not, don't guess, but it has to register in your mind. Is that clear? You don't have to redo all the calculations. But if we want to increase the frequency by a factor of 10, I got to reduce the value of capacitor by a factor of 10. But don't memorize, okay? So this is what it is. One of the most important things we use in engineering is scaling, because it's not practical to implement everything in the lab, but we scale it accordingly, extrapolate. Is that clear? That's what the so-called artificial intelligence is. Okay. And so do me a favor. Make sure you understand this. Don't blame me or Roy Tuesday. Okay, I want everybody to understand the general concept, how these frequencies occur, how we can extract the sine waves from here. Is sine wave different from cosine wave? Yes or no? I'll be, yeah. Say again.
It's a space shifted over.
Okay, what are you saying?
I said the same words you did.
Are you collaborating against the teacher, or you know it for sure?
We have
Know it for sure?
we have mental RF signal.
Oh, mental RF signal. If I give him an F grade, he gets the same thing? That's true. In other words, what it is, I'm not saying anything negative. Most important thing is, when anything and everything in nature is sine wave. Is that clear? Square wave does not exist. We made it up. The digital people made the world upside down. But when it comes to the question of filters and everything boils down to the sine wave. Is that clear? And the most important observation you should do it is, when one here have an oscillator like this, run it through the appropriate filters to see if you can extract the fundamental third harmonic, fifth harmonic sine waves. Do it before do it before. Tell me. Huh? You don't wait until the exam, madam. Is that clear? Okay. So go back to the Fourier series and see what it is. I'm not asking you to overload, but you should have a complete, clear understanding of this. And now, madam, I need the blackboard. Any questions on this, please? Oh, you are already experts? Huh? Project 1, okay. Because you see, digital doesn't exist, we made it. Hey, the whole damn nature is analog, is that clear? The digital guys made it fun, including me, okay? But if I put ones and zeros in your ear, can you hear it? Why not? So everything has to be converted back to the analog. Is that clear? No, that's what it is. Okay, the mother nature is analog. So we use the convenience for digital, we pay the damn penalty. Is that not true? Okay. Madam, can I use the blackboard? Okay. And give me another half hour. Okay, I want to go into something.
Oh, you mean the whiteboard?
No, take them out. I need the black. Thank you for all this. What I'll do, I'm going to share a part of this with our TA. Why are you looking like that? She has to know. Oh, I don't know, but this is the deal. First of all, I'll take a look at them myself. Then I will share the information with the TA. And of course, definitely I'll show it to Dr. Rohik before I return them to you. If you're trying to tell me a story, I'm going to show it to the dean. Is that clear? Did you manipulate any data?
No, I would never, Professor. I would never lie.
I didn't
No,
ask
don't
you.
lie, Professor.
Did you fabricate data?
No,
Huh? Everything is based on what you have done the design. Mike, you tell me. I don't trust these people. Okay. Right? Okay. Huh? Oh, yeah. Now, this is the deal. So, I have your okay to share with our TA, our chair, and definitely Dr. Rohik. Okay. And of course, I'll show it to the industry people too. Chances are I may, not only me, some of us. So, I'll show it to them. I'll say if they have anything to contact the department. Through the department, you'll try to get something. Okay. Thank you very much. And I'll keep them. I'm not going to return them to you Tuesday, but I can keep them, right? I'll pass it on to your TA. Even before I leave this department, I'll pass it on to TA. Okay, ladies and gentlemen. So I need to, give me a few minutes. I need to reorganize myself. Give me a few minutes. What I'm going to do is, you got a question for me, madam?
No, I was looking to see if you had a marker.
Yeah, I got markers.
I got plenty of markers for you. Where are my markers from?
Not your marker.
Ones that I gave you.
Maybe, but once you gave me, that's mine. Is that clear? What's the matter with you? If they don't try, hey, does anybody have a black marker? Or maybe?
I have red and green.
Anybody has a black marker? Yes, you have a bunch.
No. I gave them away, I think.
To me?
No, to another person.
Go and get it from him. What's the matter? Okay, never mind. Okay, ladies and gentlemen, let's talk about the next 15 minutes is extremely important. So what I'm going to be doing is the applications of bridge amplifiers. And nowadays, okay, if I write from here, you can see it? Okay. And once again, we applications of bridge amplifiers. Why I could not put it on the computer or on the canvas, part of it contains the confidential design information. Okay, so I can't expose. But anyway, follow me very carefully. A bridge amplifier. So give me 2 minutes. I'll draw the diagram first. Okay. A bridge, by definition, even though I'm drawing this as resistances, in reality they could be RLC. Is that clear? Is that clear? But I'm going to simplify it. So I got a bridge structure with 4 resistance. And I'm going to be activating it with a voltage source. I'm going to do with the DC. Afterwards, you can always extrapolate for your AC, any kind of frequencies, right? But right now, I'm using 12 volts. So you can actually modulate. So V, yes, is 12 volts DC. Okay? If it is AC, you can always will have to specify the RMS and also definitely the phase angle. Is that clear? Right now, I know DC doesn't have any phase angle. So I got the resistors. Let me follow the actual design sequence. R1, R2, R3, R4. Towards the end, I'll tell you where I got the design from. R2, R3, R4. And this node, I'll call it B and D, A and C. Okay. This is node A. This is node B. This is node C. This is node D. Okay. Now, we are going to use a series of differential amplifiers. I'm going to black box it, and I'll call it D and B. Okay, VS2 and VS1. So this is an amplifier array. So you can have 2 of them or 3 of them, whatever it is. So I got my B node. Okay. So let me identify exactly so that whatever the date count it did, I'll duplicate the designs right now. VB and VD. I'll call this voltage VB. I'll call this voltage VD. And then give me 1 more minute. Okay. I'm cheating a little bit, but it's okay. If you, okay. And the magnitude of the gain, voltage gain, is 5. So I don't worry about the sign. But system has to be stable. Is that clear? Okay. And then I'll call the output voltage V sub O. Okay, I'll put the values of R1, R2, R3, and R4. Follow me extremely careful. Okay. Steady state. By the way, all these are sensor resistors. Is that clear? Not the ones what you get for local. These are sensing resistors which are sensitive for curvature, which are sensitive for pressure, any kind of variation, temperature. So these are all steady state values. and all R1 through R4 sensor resistors. If you don't like the resistors, you can use sensor inductors or sensor capacitors, but they cost more money. The cheapest are resistors, right? Why? Why the resistors are cheaper? Huh?
Cheaper materials. Easier to fabricate.
Do you know it or wild guess?
Oh, educated guess.
Educated guess. Wow, educated guess. Why resistors are cheaper than inductors, even though inductor is a wire? Huh? Damn thing, inductor is a wire. But why? Okay, you figure it out before Tuesday. Is that clear? I don't know. No, any of them can be the sensors, okay? But I'm using the resistive sensors. Okay, R1 through R4 are sensor resistors. Steady state value R1 through R4 is 10 kilo ohms. Okay, follow me very carefully, please. Here is a resistance. This is area of cross section A. This is length L. And rho is resistivity of the material was used, whether you use carbon, whether you use something else. So resistivity is fundamental, but anyway, resistance R in ohms, pretty much universal, is rho L by A, so many ohms. Okay, is that clear? Now let's get to business. And I elongate. And I'll call this resistance, okay. So when I elongate the resistance, follow me, ladies and gentlemen. I made it more length. Same amount of mass, I elongated it, right? Same mass. Yes? This A, area of cross section. Oh, I'm sorry. Okay. A, thank you so much for correcting me. Area of cross section. This is how the resistors are made. If you don't like it, hey, if you don't like it, go to Thomas Alva Edison, wherever he is, okay? Tell him why did he make it. You don't want to go? What may be. Otherwise, believe me. Okay? Not me, the textbooks. Okay? Follow me very carefully. Keeping the same mass, if I elongate it, what would happen in the area of cross section? Will it be the same, shrink, or become more? Shrinks, becomes smaller. Everybody see that? No? Okay. So A becomes less, but my length increases, right? Yes or no? Okay, length increases, A decreases. So if I elongate, what happens to the resistance value?
Increases.
Huh?
Increases.
Increases? Did you put a flip coin? Increases? Because you want to be together? Hey, anybody wants to dispute? When I elongate it, will the resistance increase or decrease or stay the same? Huh? I'll give you one more chance. Okay. 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 Resistance increases. Everybody see that? If I go the other way around, decreases, right? Okay. Let's get out to business. Elongate, resistance increases. So I'll give you the values. I made up some of them, but basically the same trend. Okay. When I elongate, increases to 11K. It is actually 10.76 or something, but 11K, right? It increases by 1K, right? And then by the same token, if compressed and resistance decreases, everybody agree? Otherwise, go and do the experiment in your physics. Decreases. All right, ladies and gentlemen, that we are in good shape. Let us say decreases to 9K. I made up this, okay? Because they gave 9.3, 9.2 or something, 9.7 for elongation. But anyway, to make the story straightforward, if I elongate, the resistance increases to 11K. If I compress, it comes down to 9K. Is that clear? Okay, now let's get to business. My VD, which is the voltage here, this is my VD. Is it not R4 divided by R4 plus R2 times 12? This value, VD. Okay, let's put it this way. VD is equal to R4 divided by R2 plus R4. Straightforward. And if you don't like the resistive sensors, use the inductive or capacitive sensors. Is that clear? Okay, times my 12 volts. So putting the values, this is 10K divided by 20K. Why I'm doing it, there's a reason. Times 12, 6 volts. Is that clear? Right? And if I do this, by the same token, my VB, steady state, is nothing more than R3 divided by R3 plus R1 times my 12 volts. It is also 6 volts. Yes or no? Huh? Steady state. Okay. So in steady state condition, nothing is happening. I just built the system. My VD is 6 volts. VB is 6 volts. What is my V sub O, please? V sub O is nothing more than 5 times VB minus VD. Is that correct? Huh? Right? So what's my VO? Huh? What's the VO? VO? 0. Why are we wasting time for 0 volts? No idea? 0 is not doing anything, right? Then let's see what happens. I can go up to 2. Right? Okay. All right, V sub O is 0 volts. That's pretty nice. We are not wasting time for 0 volts. Is that clear? Okay, now what we are going to do, this is a bridge path. I want everybody follow me. When I say bridge, it could be a bridge on the road or anywhere. So I'm going to be putting the sensors. Give me 2 minutes because I don't want to mess up the thing. Okay. Give me 1 minute, please. I put R4 sensor here, and I'll put R2 sensor here. This is a bridge or anything which is going straight. Okay? Right? Now let's do the following. I want to make sure R2 and R4, and as per the Dade County diagram, I want to be absolutely sure about it. Okay. Yes, sir.
I have notes from when we did this.
Yeah, but why I'm putting this? Okay, you got it, right? And there's a little change. Oh, wonderful. Hey, I already did. You did it. Everybody did it?
We did the different turns, and then you had us do
Very proud of you guys.
some.
How come when 3-4 people ask me what happened? So those are the guys who cut the class, huh?
And then you told us to place R1 and R3.
Yep. What did you do it?
I wasn't sure. I found a diagram that said that they're in opposition, but I don't see how they remain unchanged.
Let's not get into that discussion. Hey, I'm sorry because you see, 3-4 people sent me an email. Professor, what is the result of that? Apparently, those are the guys who cut out. You people did it. So pretty good. So you want to continue on this? Go ahead.
Oh,
Yeah, write down. Huh?
No.
Yeah. Okay. So we already got it, ladies and gentlemen. Okay, what it is when once we have straightforward, and you can clearly see my VD is same as VB, so my output is 0 volts, right? When we come on in, hey, come on in, hey, Gabriel, come on, put it. What's the matter with you?
Yeah, Gabriel. Yeah.
Thanks, okay? So it's my, anyway, so and now I know people who are trying to trick me, right? Okay,
I would never.
go.
What am I doing?
Go ahead. No, but no, show what you got.
Okay, so this is for no turns, so this is what we just did, and this is the same math here. Nothing's compressed, nothing's elongated. If we do,
Follow him very carefully. I'm proud of him. Did you people do it at home too? Okay, good. But let's go. There is a reason why I got a static from the Dade County. Yeah, look into him.
R4 here, R2 here.
So what happens to R4, what happens to R2, then we'll move on.
R4 is being compressed, and R2 is being elongated through the curve,
Everybody see that?
and this tells us the pressure that's acting on this bridge so that the county knows when we need to shut down the roads. Or
Okay, put the R4 value, how much would it be?
R4 9 KO. R2 equals 12 K.
Okay, everybody saw that, right? Because, and as such, this is what almost wherever you have bridges, wherever you got structures where there's a possibility of bending moments, so they use the same scenario of bridge amplifier. Okay, right now you can clearly see one of them is 11K, which is R2, which is 9K. And in that case, the value of the voltage what we're developing. Put down, Gabriel. I'm so glad you people are following. Okay, so glad. Go to Dade County, say you're a great engineer. Thanks, Gabriel. You got 5 minutes to conclude. Then we got to move on. So anything and everything nowadays is control systems. Is that clear? The concept of artificial intelligence comes. They keep track of how these bending moments are for any reason. If it exceeds the limit, you stop the traffic. Is that clear? Make sure. Is that clear? Because we people design things which are being used by the public or for hospitals, whatever it is. So that's what it is. You got to have. So in a bridge structure like this, thank you, Gabriel. Even though you're failing the course, I'll let you pass.
Oh, thank you. That's very generous.
Okay? And so anything and everything nowadays is control systems, but you don't have to go to the physical location of a road or bridge or any place, right? What happens if your lift gets overloaded? David, you tell me. You're supposed to be an expert on that. Suppose the elevator's going up to 3rd floor here. It's okay. We can jump out of a 3rd floor. Think about a building 40 stories.
You jump out?
Yeah, what do you do if the bridge is overloaded? Not bridge, The elevator is overloaded.
The thing just falls straight down. Right?
Now then, who is responsible if somebody gets killed?
Oh, the university.
What?
Yeah.
Get him out of the...
No?
Now it is our responsibility, whosoever installed it, whosoever put it. Yeah, right now the artificial intelligence is taking over. So you got to be able to predict the failure modes. Is that clear?
Yes.
You hire me as your assistant, sir. Okay. Now what I'm going to say, ladies and gentlemen, the engineering what we went through is going to be in a new phase right now. That includes you also, young lady. Okay. Right? Looking at me, putting the thing doesn't help. Catch. Okay. Okay. Now everybody understood this, right? So artificial intelligence is nothing more than prediction in a proper way, right? So if I increase the bending moment, apparently this is going to collapse or do some kind of harm. Okay. So one of the things they always say is it's the responsibility of engineers or people who do this, such that these things won't happen. You want to come in, madam? Come here. She is our chairperson. These people, come on in, madam.
Okay. All right. I just wanted to say hello. I know this is his last lecture, and stop by and
So
say hello
sweet
and
of
thank
you.
you.
All these people are giving me trouble. So what do I do with them?
Oh,
Huh?
all A's.
Madam, I don't. My teachers, my German teachers told me how to write grades from D, E. I don't know how to write ABC.
Uh-oh.
She gave me an opportunity to continue here, and as so nice of all of you to say bye to people like me. And this institution has a much more trajectory. It all depends on you people. Tell her to be nice to me, to buy me a cup of coffee.
I'll buy a cup of coffee.
All
Not
right,
you.
okay.
If you want to say something, go ahead, madam.
Oh, no.
Hey, by the way, some of them are going to the grad school,
Oh, good.
but they don't have dinero.
I'm working on it.
She is our chairperson. She wanted people like me to continue,
Yeah.
but I sought her permission. This is going to be my last semester, as I said, because I want to spend time with the family, and I'm going to run away from my wife. Wow, could you see that? And FIU has given people like me a career, a path, an objective in life. And one thing as engineers, you should always keep in mind, never sacrifice ethics. Even if your boss or supervisor tells you to do something, madam, which is not engineeringly acceptable, stand up. Is that clear?
Yes, sir.
Never. If you need any help, call me and I'll help you, and I charge $100 per minute. And she has been so kind.
Oh, thank you.
She gave me a temporary office. I mean, I got so many temporary offices, but always very nice and smiling and appreciative. And David is recording all this. He's going to blackmail me. Did you discipline me, madam, the other day? No?
No. This is historical. I want you guys to know that this is historical. This is his last lecture, and and you're getting to witness this. He is a founder of this department years ago, and he's helped build the department to what it is today. It's great because of him.
Oh, no, madam.
And his family. He can't do it without his family, right? And so this is his last lecture. We don't want him to go, but
Thank
he's
you.
leaving us, and you are very fortunate to have learned from him.
And I'll step out if you want any complaints, talk to her. I'll be outside.
I never get complaints.
Yeah. Go.
Hey,
What you people are up to?
We didn't know you were coming.
Huh? They won't let me go.
his family said no. His family said he has to leave, and so this is it. Oh,
Thank
come
you.
on.
Thank you, madam.
Come on.
Thank you, dear
Come
madam.
on.
Oh, gee.
Oh, wow.
Look at all the... They don't want to hire me. Oh, So
This is
sweet of you,
a
Ellie.
little
So
something from all of us here.
oh,
We will miss you.
Very much so.
We don't want you to go, but those ladies over there need you more than us.
Exactly.
Okay?
thank you so much. Okay, but make sure if these people qualify, give them a job.
Okay, we'll do that. They just have to show up on time.
More than them, I need a job.
You need a job as well?
uh.
Okay, send me your resume.
I gave it to her.
Remember, sir, I need you to follow procedures, go through my career.
See that? I'm going to keep it here. Don't smuggle it. Thank you so much. It makes people like me feel good. FIU has come a long way. When I joined, it was 1.5, actually 2 buildings and a bunch of sheds. Engineering started in sheds. Now we are 104 buildings and 4 campuses. And the provost was telling the last week, we 48 to 52,000 students, and the whole faculty, staff, administrators, everybody, we are close to 64,000. Could you believe that? And we are second largest in the state of Florida. 38 or 39 out of 850 colleges and universities in the United States. And I feel proud, I feel kind of satisfied that people like me grew with FIU. Whatever we have done, you students keep that tradition, move forward, okay? And God bless you. The only thing I cannot do is give you free grades. Is that clear?
You give me a free F.
Huh?
You give me a free F.
That I can give you. I can close my eye and write. Thank you, madam.
Oh,
You made my day.
All right, thank you.
Thank you so
Thank you
much.
for your service.
No problem.
Thank you for your service. And thank you to the family. Thank you.
Yeah, they have been so much helpful to me.
Can we get a group picture?
Okay, come on in. And why don't we get all the students? Come on in, please. Yeah, everybody come on in. So you can't say we don't know Subbarao, okay? Come on in. Thank you, David. Come on, everybody. Madam, you made my day.
Oh, no. Thank you. Thank you. Oh, thank you. Oh,
No, you made my day, madam.
oh, no. Thank you. You built this. This is what you built.
Watch these 2 girls, big troublemakers. By the by, if you have any opportunity,
Oh, thank you.
madam.
Daddy,
Okay.
you in the middle.
Oh, okay. Don't smuggle my pants. Oh, boy. Come on in, madam. Come on in. You know, it made my day. Thanks, Dave.
Come on. Yeah. Yeah.
Sorry, I don't mean to cover you. You got room?
I got all I can get.
I didn't know you were planning all this.
She helped me.
I did.
Okay. Thank you, madam.
All right, everyone. Cheese.
Thank you. It's a great help.
All right, now one crazy one.
Thank you.
Thank you.
Thank you. Thank you.
I want to thank everybody. Make a great career for yourself, right? Yeah.
All right.
Still, now you can think about
I
giving me
will.
a job.
I will. I will.
Thank you for this. You people have been so kindly helpful.
Oh, thank you. That's good. Thank you. Oh, thank you.
Thank you so much.
Thank you.
It's okay. Hey, it made my day. I can't speak anymore. I can't speak anymore now, right? Okay. If you need anything, talk to Gabriel, okay? All the best. And one thing you should always keep in mind, not only at FIU, when you become a career-bound person, follow the science, follow the engineering, follow the ground rules. Is that clear? You know, you can't do that like that bridge.
Okay.
If you kill somebody because of your lousy design, you can't get that life back. Is that clear? Same thing, you know, one of the most important things we are taught in engineering ethics, even before ethics started as a course, almost 65 years ago, my own teachers said, if something is not scientific, if it does not work, no matter who you are, stand up. Is that clear? We have a responsibility as engineers, that's number one. Number two, the procession of engineering is everlasting. Things keep on changing, and never forget your institution where you have come from. Never forget your parents who supported you, right? And be proud of yourselves, right? And if you want to get a free grade, and you can always negotiate with me in the parking lot.
I'll see you there.
And I need dollar bills.
Hold on.
Dollar bills, $1,000.
1,000?
Yeah. You want to ask me any questions about not the subject? I can't speak anymore because I didn't expect any of this happening. But you want to ask me anything general about procession or profession or what you want to do? Yes, sir. You want to drop out of the college? We won't let you because our salary is dependent on how many students we have. You got any question for me?
He has a question.
You have a question? Yes.
For going on into grad school, how do you find and choose the right path of study?
I'll answer that question. Did you understand what he was asking? Stand up and say, then people can. No, I'm going. I'm going. No. Actually, I'm going to give you because I have gone through that. Go ahead.
For continuing on, either in work or in grad school, how do you choose the right path of study or focus?
Okay, I'll answer. Anybody else has a question? You got a question for me, right? You want to drop out of the school? No graduate school? Yeah, go ahead.
What GPA do you need to go to grad school? Is it like a minimum GPA?
Huh?
Is it like a minimum GPA for grad school?
Shall I be really honest with you?
Yes.
University regulations require that you should have at least a 3.0 average and 4 scale. But if you have got numerous applications and less amount of graduate positions, we cheat. We raise the standard. But the state-wise, the requirement is that you should have a 3.0 out of 4 to be considered for grad school. But for any reason, maybe sickness, maybe something happening in the family, maybe your GPA dropped down. But that should not prevent you from going to grad school. So go to the professor or the departmental chair like her, explain, hey, this is what it is. Give me a semester or 2 to bring up my GPA. Okay, then they will admit you into the grad school program. Because if you have to get an assistantship, you have to have those minimum standards. Is that clear? But if you are slightly below, don't let that pull you down. Okay? So explain to the, mostly you should contact the counselor and the departmental chair. And a lot of times people have made those kind of adjustments. But if you're a continuous loser, look into my eyes, sir. Huh? Bye for good, right? Now usually, because this is a state institution, we are funded by the state, so we have an obligation to make sure that you people come up, but at the same time, there's no manipulation. But there's always an exception. If something is not right, give a second chance to, right, improve. If you don't improve, I didn't say that, but that's state. Okay. And one thing you don't want to do, ladies and gentlemen, when you go to grad school, correct me if I'm wrong, young lady, if you go to grad school, you have to have a focus what you want to be after, okay? It's not that you just pick up something and do some kind of a research, forget about it next moment. Because in the grad school, the graduate students were invested by the companies or by the government or whatever it is. So they expect you to put back the thing into the system, okay? Is that clear? Whether it is the industry, whether it is a hospital, grad school, academics. So you have to have that kind of a commitment for yourselves. That's number one. Number two, believe me, when you go to grad school, it gives you a lot of satisfaction. There's so much abundance to learn. And each of us, including me, as faculty, we learn from students. That's an opportunity you have. Come on in, madam. That's an opportunity that has been provided in the field of academics. And when the university, yes, madam, you got a question for me?
No, I was just going to comment.
Okay. So this is what the history says when the institutions like Princeton, MIT, Harvard, and all these institutions started, they made it a point to make the academic institutions independent, not under the control of politicians. And even today, same trend is continuing. And among yourselves, you outshine yourselves. It's an opportunity. Go to grad school or whatever it is. And good luck to you people, right? I'm running away from my wife and from my home. But don't bring me back to her, okay? And if you misbehave, I can change the grade with 1 year time scale. Yeah. Yeah. What? So you better be nice, right? Yeah. Thank you. Thanks for.
Yeah, we can email you for the next year.
Huh? What do you want to give? Anything has to be in dollar bills. Is that clear? No. Thank you very much. Thanks for the opportunity people gave people like me. My colleagues all retired. Dr. Jim Story, who started this department, Dr. Malcolm Heimer, who actually was the inventor of the pacemaker in this building. Could you believe that? And I was trying to contact him, but he's so busy going around in California. Wanted to get him on the video, but he said he would come in the first week of May. By then, you guys are gone, right? Unless you fail this course and repeat it. No?
That won't happen.
Huh?
That would never happen.
That will never happen.
You wouldn't let us fail, right, Professor? Not your favorite students.
You know how hard we work.
So you already tracked down the trajectory of Dr. Roeg and me. We won't fail the student. That doesn't mean we let everybody pass. I requested some of the people to drop off the course where they're not making it. And I don't know whether they got the, how many, but they got the refund from the school or not. How many weeks you had to be in to get the refund back? Huh? I don't know. I
You get your
don't.
money back like the second week, I think.
Week, oh, that's all?
Yeah. To get like the full refund.
No, not week. After first test and after.
The next Monday, so like the second Monday, you can get the refund after that.
Okay, but anyway, after test 1 and after quiz 1 and 2, then I told some of the people, I mean, it's better not to get a failing grade. I don't get involved in the money, right? Okay, good luck to you people. I'll see you Tuesday. You want a simple exam or complicated? No wonder. Hey. I'll give you a complicated exam and show it to Dr. Roig. Even if you make a spelling mistake, -5. Yeah? No? Study hard. God bless you. I may not get to see you next semester, even though the people are asking people like me, but let younger faculty take over. I want to spend time working for my wife. Okay, so she can keep me in the house, and I'm going to run away to my daughter's place and my son's place in North Carolina. God bless everybody. Bye-bye. Thank you. There's a $100 bill here.
Really big one.
You took it off?
Yeah.
Thank you. I personally, on a one-to-one basis, I thank you. Bye-bye. Bye, everybody. Madam, come on in. Don't give them any passing grade, madam. So I'll come to your office possibly, definitely Tuesday. Then give me their,
Here Tuesday.
huh?
I'm not here Tuesday. I'm going to conference.
So you want me to come Monday?
I'm leaving on Sunday. I'll be back on Friday.
When are you going to come back?
Next Friday.
Do me a favor. You have my email.
Yes. I've
Make
already
sure
got
these
it.
people don't tap it. So send their grade to me on a maximum points of 60.
Okay.
60 is the max.
Okay.
Okay? And scale it down. And I know all of these people are zeros, but anyway.
I wanted to ask you for something outside.
Okay. Hey, he's putting me in trouble. Come on, okay. Thank you. God bless. Miss, she's a wonderful lady. Make sure she will continue as your TA and a faculty down the line, okay? Don't give her a hard time. So I could sustain, not her, okay? Okay, I'll be staying outside. Madam, and good luck to your conference, but I'll stay in touch with you. Send me that email, okay?
See you on Tuesday.
Popeye, come.
If anyone has students after class and they're okay with being in front of the camera to speak a few words about your professor,
Okay, I'm getting it. I'm getting out. Popeye, come on in.
just hang back a little bit and then we can get that done.
Thank you so much, Eric. I'm getting out, okay? David, don't recommend giving them a passing grade. Is that clear? You saw how much trouble they are giving faculty like me, huh? Let me get out, madam. Hey, I paid you for life. What's the matter with you?
Put a pen inside.
No. This pen won't write gift for you.
Thank you.
This pen writes halfway. Hey, this pen may write or may not. This is gift for all of you.
Thank you.
Okay.
Thank you, Professor.
No problem.
Nice to be in your class. I will use it.
Okay,
Nice to be in
David.
your class. Nice to meet you.
Okay. Take this, madam.